In this lesson, I will be talking about proof by induction. And to understand the concept of induction, I'm going to take this one example here of a real-life situation where you have a line of dominoes, as I've shown. So the dominoes are numbered 1, 2, up to number n, which is the last domino here. And I'm going to use the notation k for some random domino here in the chain. And k plus 1 is therefore the one after it. Okay, so there you have it, a set of dominoes all lined up, and from 1 to n, and k, as I said, is any random domino between 1 and n. Now, and in this example, we're going to try and see the big picture in terms of what has to happen for all the dominoes to fall. And if you think about it for a moment, there are two simple things that we have to be certain of to make sure all dominoes fall. And the first thing is, it makes sense that the first domino has to fall. I mean, if the first domino doesn't fall, the whole chain doesn't start. Secondly, if the first domino falls, there is no guarantee that all the other ones will fall, unless, of course, they're close enough together. Now, as you can see in the diagram, I've drawn them close together here. But in terms of the general notation of k, k plus 1, etc., what actually has to happen. And what we're going to say is this, the first domino has to fall, that's the first thing. But the second thing is, if any random domino k falls in the chain, the one next to it has to be close enough. K plus 1 has to be close enough to fall as well, where k stands for any domino between 1 and n. So if you think about it, they are the only two things that we have to make sure of. And if we make sure of those two things, we basically can be certain that all the dominoes fall. So let's go down here and let's look at that summarized, so that idea. So what I've done here is I have, as I said, only two conditions must be satisfied to knock all the dominoes in the chain. The first domino must be knocked, as I just said there, to start the chain off. But once that falls, the gaps have to be close enough for all the other dominoes. And the maths way of saying that is any domino k must be close enough to the next one, k plus 1, to knock it over. Now, if you get that basic idea in relation to dominoes, it's the exact same idea for the rest of this topic in maths in terms of proof by induction, which we use as a technique of proving certain statements in maths. So that's the idea, that's the basic idea behind mathematical induction. Now, let's take our first example in relation to that. And we can go straight to an exam question that was asked a few years ago. And the exam question was this: prove by induction that the sum of the first n natural numbers, 1 to n, is given by n into n plus 1 over 2. And we start off, a good technique is to say we have a statement we're trying to prove and give that statement a label or a name. We'll call it proposition, a statement or a proposition. We'll call it PN for short. Proposition n or statement n states that 1 plus 2 plus 3. So we're just merely stating the problem that we're trying to solve up to n. If you add all those, you end up with n into n plus 1 over 2. Now, if we compare this to the dominoes, the first thing we have to prove is that the first domino falls. The equivalent here is to prove that P1 is true, statement 1, where n is 1. So statement 1, proposition 1. What would that say? Well, let's look at these more closely. So that's term 1, term 2, and term 3 in a sequence all the way up to term n. So if proposition n means all the terms of the term n, well, proposition 1 means all the terms of the term 1, which is just term 1. So term 1 is 1, and that should be equal to, on the other side, if this is true, n is 1, so 1 into 1 plus 1 over 2. So now we have 1 on this side is equal to 1 and 1 is 2 over 2, which is 1. So that's true. So by proving that, that is the equivalent to proving that the first domino has fallen in the chain that I showed you earlier. Now, the next thing we do, if you think back to the dominoes, we went on to any random domino k. As we said, if any random domino k falls, it knocks the one after, which is k plus 1. So, and there's a big if there, of course, if domino k falls. And we are going to talk about that now. So let's call that proposition k. So let's assume it falls for the moment. We're not proving that it falls yet. We're just assuming that domino k falls. What does that mean in terms of this sequence? Well, it means that 1 plus 2 plus 3 all the way up to domino or number k would be equal to k into k plus 1 over 2. So again, that's term 1, term 2, term 3, up to term k. So there's a slightly different meaning for k and n. They look the same, pn and pk, but again, to remind ourselves, k is any random domino between 1 and n. N stands for the last domino in this sequence here. So there's, even though they look the same written down, there's a slight difference in meaning. Okay, so that's proposition k. Now, we're going to do a straight thing at this stage for a moment. We're going to assume this is true. So we're going to assume that's true and see where it leads us. Now, if you assume that's true, let's see if it knocks the next domino, which is k plus 1. So we're going to move on now to k plus 1 straight away, if we assume that for the moment and see where it leads us, as I said. So proposition k plus 1, what would that be? Well, it's 1 plus 2 plus 3 all the way up to k plus, we go up one extra now, one term after k, which is term k plus 1. So that's up to k plus 1. And let's number those terms again. Term 1, term 2, term 3, term k plus 1. Now, that should be, if all is going right, that should be the same thing as putting in k plus 1 on the other side as well. So everywhere you have k, put in k plus 1. So it's k plus 1 here, multiplied by k plus 1 over 2. So what I've done, just to highlight what I've done there, k has become k plus 1. When you go on to pk plus 1, everywhere you see k, you substitute k plus 1. So that's the big change on that side. And we can tidy up that. So that's k plus 1 into k plus 2 over 2. Now, the problem here is this is what we're trying to prove. We haven't proved this yet, so we put a question mark to say that we're trying to prove this. They're not equal yet, basically. The next step is to use something that we have assumed, which is pk. And I want to just highlight something else on this side now. If I highlight from 1 up to k, that's obviously the same as 1 to k here, which we have assumed is the same thing as this. So that means it's reasonable now to, if these, everything I've highlighted in green are all equal to each other, we can substitute what's in the circle here for this, for what's in green highlighted here. So we can now replace 1 to k with k into k plus 1 over 2. And don't forget, we still have the plus k plus 1 hanging on at the end here. So this k plus 1 is at the end. And now that's, we'll call that the left-hand side for the moment, LHS for left-hand side. And we're trying, the whole point is to prove that's equal to the right-hand side, which is over here. Now let's tidy that up. So again, what I've just done, just to highlight, what I've done is I have replaced this with this, because we assumed that they were the same in the pk step. So we're seeing where our assumption leads us for the moment. Now, let's just tidy up. So if we tidy up, we get k into k plus 1 over 2 plus k plus 1. Put that over 1 maybe, and get a common denominator of two fractions. 2 is the common denominator. That's k into k plus 1. 1 into 2 goes 2 times, so it's plus 2 into k plus 1. Now we can take out the common factor. There's a k plus 1 on both sides, on both terms there, I should say. Take that out outside the bracket, and you have now got k plus 1 times k plus 2 over 2, which is the right-hand side. If you look at the right-hand side up there. So we'll just say that it's equal to right-hand side. In other words, we have proved that the proposition or statement k plus 1 is true. Of course, there's a big assumption built in there still. In getting there, we assumed that pk is true, which we're not quite entitled to do yet, but we assumed that pk was true. Now, but in the same way as if we go back to the dice, or sorry, back to the dominoes, I should say. When you knock the first domino, that's one part of the puzzle fixed. When you can prove that any given domino will knock the one next to it, if you assume that any domino k will knock the one next to it, that in itself, none of those in itself will prove it, but the two of them together will. Because the first domino is not an assumption, that definitely does fall. So what if k was 1? If the first domino falls and any domino knocks the one after it, which is what statement 2 says, well, that means that if the first, going back to our question, if P1 is true, which we proved earlier, I mean P1 is true, if we combine that with the second statement that pk plus 1 is true, assuming pk is true, well, that means that P2 is true, because that's the equivalent of k plus 1. Now, 2 is our new k the next time around, so P2 is true. Now k is 2. That implies that pk plus 1 is true again, which is P3 is true. And basically, this is the equivalent of all the dominoes toppling after the first one has fallen. So as I said, there was an assumption built in, but you don't have to assume anything with the first one because the first one definitely falls. We proved it up here, that P1 is true. We saw it there. So that's no longer an assumption. And if you start from there, and as I said, pk plus 1 follows from that, which is P2 in this case. P2 makes P3 true, etc., which means that Pn is true for all values of n. For all values of n. And there's a nice way of saying this actually, for all values of, you can use this symbol here, for all values of n. And that's it, that's the proof done. We have now proved that the statement is true, and that's our exam question completed.